So the nice is a matter of taste, but I'll say, nice thing about working in polar form is it leads to some fairly approachable formulas for dealing with products and divisions of complex numbers. And we'll see later as well that it leads to ways you can talk about roots and powers of complex numbers as well. So here, if we have two complex numbers, z1 and z2, their product has form r1, r2, that is the product of the moduli, times cosine of theta 1 plus theta 2, that is cosine of the sum of the moduli, plus I sine of theta 1 plus theta 2, where z1 over z2 has form r1 over r2, the quotient, that's the word I was looking for, division of quotient of the moduli, and cosine and sine in terms of the difference of the arguments, cosine of theta 1 minus theta 2 plus, I sine of theta 1 minus theta 2. And I'll show you a little bit here about how we get that first one. The second one's very similar, but a little bit clunkier, just because division takes a little more subtlety. But for z1 times z2, you have r times cosine theta 1 plus I sine theta 1 times r2 cosine theta 2 plus I sine theta 2. Multiply them in, you can just immediately pull out the r's, because you got a whole bunch of r1s and r2s. They don't really stick on anywhere nice, just pull them to the front. Then you will have cosine of theta 1 times cosine of theta 2, first terms, plus I cosine of theta 1 times sine of theta 2, first times second, plus I sine of theta 1 cosine of theta 2, second times first, minus sine of theta 1 sine of theta 2, which comes from the seconds being multiplied and the I being squared, leaving a negative 1. Then from there, you just regroup those, where you have cosine theta 1 and cosine theta 2 getting stuck together with the difference of sines, and that is one of those sum of angles formulas for cosine, while you pull out an I and you have the cosine sine and sine cosine is the sum of angles for sine, giving you that formula. And we'll see with something called de Moivre's theorem, a way that we can extend that. But for now, let's get some quick examples with these two formulas. So here, we want to find the product and quotient of the complex numbers z1 equals 50 cosine of 4 pi over 3 plus I sine of 4 pi over 3, and z2 equals 5 cosine of pi over 3 plus I sine of pi over 3. That is, we want z1 times z2 and z1 over z2. So for the first case, the product, well, this is going to be a little long if we want to do it by hand, but thankfully we do have this formula here to help us out. We have r1 times r2, where that would have form 50 times 5, multiplied by cosine of theta 1 plus theta 2, where here theta 1 is 4 pi over 3, and theta 2 is pi over 3. Then we're adding to that I times that same sum of angles. Sine of 4 pi over 3 plus pi over 3. And then it's just a matter of simplifying. So once you get the formula, it's very nice to work with. We have 250, and you do the formula, math's not very hard, is it? Times cosine of what will end up being here, let's see, not actually use a parenthesis in there because I already used one. You'd have 4 and 1, so 5 pi over 3 plus I sine of that same value, 5 pi over 3. So we would have a modulus here of r equals 250 and an argument of 5 pi over 3, for the product, or if we wanted to, we could evaluate that to get it into our rectangular form. And there are some bits of creativity you can do where you can translate between those rules or derive this kind of rule in terms of the rectangular form, but we're not going to worry about that too much for now. For our second part of this, z1 over z2, we will just have r1, 50, over r2, 5, multiplied by cosine of 4 pi over 3 minus pi over 3 plus I sine of that same difference, 4 pi over 3 minus pi over 3. So 50 over 5 would leave us with 10 times cosine of pi plus I sine of pi. And this is actually a kind of important argument to bear in mind, because when we're along the y-axis, remember that cosine is always 0. That is, cosine of pi is always 0. And sine is always 1. So this would just be 10i. That is a purely imaginary number. It's an important little thing to consider here. It's an important case to bear in mind. Anyway, we're going to finish this section with a discussion of how we can talk about powers and roots, but I think we've seen quite enough getting to this point that we'll mostly just focus on the powers. I'll mention the roots as well, but you don't need to worry about that quite as much.